Back. So we've been talking about the L1 CDFT. And we'll continue doing that. Okay, so today what we want to do is we want to talk about differentiation and the CDFT, okay? And you can think of this in one of two ways, at least two ways. One is that, you know, it gives you the way of relating the CDFT of a signal and its derivative in the case when it's differentiable in a suitable sense. But I think a higher level way of thinking about it is that you want to understand the relationship between properties of a signal and properties of its CDFT. Okay, so we're going to sort of explore it from that angle as well. Okay, so I'm going to give a fairly general version of the differentiation results, sort of more general than you typically see, because it's not altogether that much harder to prove than the one normally sees, and we're going to make use of it later, and I think it provides us with a nice illustration of using some machinery. Okay, so what I'm going to prove is the following. So let's let f be continuous and t periodic. Okay, and I want to re-emphasize here, I said this when I talked about periodic signals, but when I write this means periodic on the whole real line. Okay, so this means that from 0 to t, the value of whatever f is at 0 and t, it has to be the same because it needs to be periodic. So I can't have something that looks like that, right? The values at 0 and t have to line up. Okay, so this means periodic on the whole real line. Okay. So let's let that be true, and suppose that there exists an f prime in L1 of 0 to t such that okay, f of t is equal to f at 0 plus the integral from 0 to t f prime of tau d tau. Okay, and this is true for every t in 0 to t. Okay, so f prime need not be periodic here. F prime, sorry, f prime is in L1 of just 0 to t, and what I mean is that we're going to extend f prime to be in L1 per. Okay. Just by translation. Okay, so f is going to be some thing defined on 0 to t, and then we're going to periodically extend it. Right, so I'm going to identify f prime with its periodic extension as well. Okay, and so then what this is saying is that on 0 to t, f is we've seen this idea before of f being the indefinite integral of an integrable function, means that f is not just continuous, but it's absolutely continuous. And so the idea is that f may not be differentiable, Okay, but its derivative exists almost everywhere, and but its derivative exists almost everywhere, and almost everywhere it's equal to the values of this L1 function f prime. Okay, so this is the the vague version of the fundamental theorem of calculus about integrating derivatives and differentiating integrals. All right. Okay, so that's our setup. So then what we want to do is we want to relate the CDFTs of f and f prime. Okay, again, thinking of f prime as being periodically extended. All right, so what's the formula? Okay, then the CDFT of f prime at n over t is 2 pi I n over t times the CDFT of f over t. Okay, so there's kind of a mnemonic for remembering this formula, and this isn't the proof. Okay, so this is just some chatter. Okay, so remember the idea when we talked about CDFTs, when we were talking about heuristically about what the CDFT was. The idea was that we wrote f as a linear combination in infinite, and that's why it kind of doesn't make sense generally. An infinite linear combination of harmonics where the coefficients were the like so. Okay, and I don't really mean equality here, but generally that sum doesn't converge in any meaningful way. All right, but assuming that that's okay, then to differentiate this, so taking an incorrect expression and differentiating it. Okay. What are you going to do? Well, you're going to, since we're able to do whatever we want, we're going to take the derivative inside here. Okay, and then we're going to get 2 pi I n over t. Sorry, we need to put the sum outside. Okay, so it's a 1 over t sum, and in z 2 pi I n over t cd of f in t e to the 2 pi I n t over t. Okay. And so then, by the same justification that, we wrote this formula, we can conclude that these must be the components of the CDFT of f prime. Okay, so that's kind of where that formula comes from. But like I said, that's certainly not a proof. We'll do the proof now. Okay, so first, let's look at the n equals 0 case. All right, so the CDFT of f prime at 0. Okay, so this is, by definition, the integral from 0 to t f prime of t dt, right? Because the 2 pi I n t over t is 1. Okay, so this, right, so now you can integrate this quite easily. So this is f of t minus f of 0. Okay, and now we're going to use the fact that f is periodic, and we conclude that this is equal to 0, and so that's the right formula in the case of n equals 0 here, right? All right, so now for n not equal to 0, what I'm going to do is I'm going to invert this relationship. And so what I'm going to calculate is I'm not going to calculate the CDFT of f prime in terms of that of f. I'm going to do the opposite thing. I'm going to divide by that. All right. So I have f CD of f n over t equals, by definition, the integral from 0 to t f t e to the minus 2 pi n t over t t. Okay, so now I'm going to stick in the definition of f prime. Right, and this is the integral from 0 to t, integral from 0 to little t, f prime of tau, d tau. Okay, then I'm going to multiply that by e to the minus 2 pi I n t over t dt. Okay. Okay, so this is a double integral, and I'm going to calculate it using Fubini's theorem to change the order of integration. Okay, so the integral here is happening in the tau t plane, right? So this is a double integral of tau and t. And if you take a look at what's going on when I do this integral, the way I've written it here, I'm first integrating with respect to tau with t fixed, and with t fixed, you're integrating from 0 to t. And so if this is the line t equals tau, this integral is being done along with t fixed, right? So along horizontal lines like that. Okay. And then after I do the integral along these horizontal lines like this, then I integrate along t from 0 to capital T. Okay, so I have a capital T here, and a capital T here. All right. So the point is that the integral is over that region there. Okay. And so when I swap the order of integration from doing tau first then t to doing t first then tau, when I'm integrating with respect to t with tau fixed, I'm going from tau to capital T, like so. All right. So I need to switch the order of integration like that. Okay. So I'm going to go integral from 0 to capital T. And then so first inside, I'm going to do the t integral. And so f prime of tau is constant with respect to that. So it's going to be f prime of tau. Then the integral, and as I just said, I need to change the limits from tau to t, e to the minus 2 pi I n t over t, t, all right, and then d tau. Okay, all right, so now this integral is easy, so do it. So I'm going to get minus, so when I integrate, I'm going to divide by all that stuff. Okay, so it's going to be minus t over 2 pi I n. All right, and I'm going to get the integral from 0 to capital T, f prime of tau. Then it's going to be times the stuff I get when I integrate. And so it's going to be, so I've done the division there. So it's going to be this thing evaluated at the upper limit of t and the lower limit of tau. And at the upper limit of t, it's 1. Okay, so 1 minus e to the minus 2 pi I n tau over t. Okay, and then d tau. All right. Okay. So let me just sort of reorganize this and swap the order here to kill that sign. So this is t over 2 pi I n integral from 0 to t f. So, whoops. Integral from 0 to t f prime of tau e to the minus 2 pi I n t over t, sorry, tau, d tau, right? And then minus t over 2 pi I n integral from 0 to t f prime of tau, tau. Okay. Now, this integral we already calculated up here, right? So when we calculated the CDFT of f prime at 0, and we decided that that was 0 because of the continuity of f. Okay, so so this one is 0, and so we get exactly what we want, right? Because this is now the CDFT of f prime. Okay, good. So that's a very general formula for how the CDFT is related to of a signal is related to the CDFT of its derivative in kind of the most general way that, at least for an ordinary signals, that derivatives can exist. Okay. Good. So what do we really care about here? Well, what we really care about looking at this formula, okay, is so this tells us, so we know that f prime is in L1, okay? And so we know by the Riemann-Lebesgue lemma that these coefficients go to 0 as n goes to infinity, which means that these go to 0 as n goes to infinity. And so what that means is that the coefficients of the CDFT of f have to go to 0 faster than 1 over n, because we're multiplying here by n, right? And so this gives us some information about the rate of decay of the CDFT of f when f is essentially differentiable. Okay, so first what I want to do is I want to first write a formula, not just assuming that f has a derivative, but when f is r times or k or whatever times continuously differentiable. So I want to basically take this result and I want to apply it recursively to higher and higher order derivatives of f. Right. So what you get when you do that is you get that if f is k times continuously differentiable and periodic, okay, and okay, so what I want to do now is I want to assume that the top derivative of f is has the same properties that I had for f itself here. Okay, so I'm going to assume that f is k times continuously differentiable, and I think it's going to be more convenient here. Sorry for me to use k minus 1. Okay, and so k here is a positive integer. Okay, and so sorry, I need to be careful how I say that. Okay, so I'm gonna, I apologize. Let k be a positive integer. Okay, so then given that, if f is ck minus 1, and if there exists some function f, and I'm going to call the function fk in L1 per 1 of 0 t c. Okay, so this is just like what I had up here, and what I had up here is the case where k is equal to 1. So k minus 1 is 0, and then this is f1. Okay, so there exists something like that, so that the k minus first derivative of f. Okay, all right, so I know that this is a continuous function. Okay, so f is ck minus 1 is equal to f k minus 1 of 0 plus integral from 0 to t f k of tau d tau. Right, so this is the same kind of formula that I wrote above, but now I'm using higher derivatives. Okay, all right, then, okay, I have the CDFT of this thing now, but of course this is only defined on the, and I need to always be careful here in this periodic case to specify that t here is between 0 and t. Certainly this doesn't hold on the entire real line. Okay, just over a single period. And so here I'm going to do like I did before. I'm going to take fk and I'm going to take its definition on 0t and periodically extend it. Okay, and then I'm going to calculate the CDFT of that. Okay, and again, you get the same kind of formula, but now you're going to get, because you're going to do the same calculation as I did above, you're going to do that k times 2 pi I over t. Okay, I think I have that right. Oh, sorry, I have the n. I apologize. Maybe something didn't feel right. 2 pi I n over t, and then I'm going to take that and I'm going to multiply it by k, or raise it to the power of k because we're doing this k times fcd of f at n over t. Okay. And so the point is you get this factor that comes out front now, raised to the power of k, because I do this computation from the previous results, k times. All right, so sorry, I bumbled over that a bit, but that's the result. Okay, and so let's look at the reasoning that I had in the previous case. All right, so fk is in L1, and so this is in L1 per when I periodically extend it. So I know by Riemann-Lebesgue that as n goes to infinity, these things go to 0. So that means that as n goes to infinity, these things go to 0. All right, and so what that means now is that the CDFT of f as n goes to infinity has to go to 0 faster than 1 over n to the k, because I have n to the k up here. All right. Okay, and so we see here that we get very nice statements about the rate of decay of signals given the regularity of the signals. Okay, all right, so let's try to write a little summary here of rate of decay of CDFT. All right, so we're going to kind of write a list here of conditions for the rate of decay, going from slowest to fastest. Okay, so if f is in L1, then I know that the limit as n goes to infinity of the CDFT of f and t is equal to 0. Okay, that's just the Riemann-Lebesgue lemma that we sketched a proof of last time. Okay, now I mentioned something last time, but we haven't gotten to it yet, but this is the right place to state this condition. And that is that if f is in L2, then the CDFT of f is in little l2. Okay, and this is a rate of decay condition, right? So this just means go to 0, and as I indicated last time, you have no real control over the rate at which the CDFT goes to 0 here. Okay, but being in L2 means that it means that you must have this, right? Okay, so this immediately gives you some decay rate conditions on these as n goes to infinity, because this thing has to be summable. Okay, so the rate of decay here has to be like faster than, or 1 over n or something, in order to guarantee that you get convergence there. It doesn't have to be as strong as 1 over n, but it can't just be arbitrary is the point. Okay. All right. Now, next, we have the case of some regularity. Okay. So if f is in CK per t, all right. Okay, so that in particular includes the little corollary here, right? So if f is in CK per, then certainly I have a function like this, namely the kth derivative of f, the actual kth derivative of f. Then I know that I have a decay rate condition here. Okay. Then what I know is that the limit as n goes to infinity of n to the k times the CDFT of f at n over t must equal 0. Okay, so this tells me that the CDFT has to go to 0 faster than 1 over n to the k, right? Okay, and so particularly then, if f is in C infinity, okay, and I want to reiterate, when I write c to the k per, that means that this is ck on all of R, right? And so, when we talked above about f, what it meant for f to be in C0 per, right? So the value at the endpoints here has to match up. Well, when I write CK per, that means that has to hold not just for f, but for the derivatives as well, right? And so for C infinity, that means that holds for all derivatives, right? And so if f is in C infinity per, then this has to hold for every k, of course. Okay, so this means that the CDFT has to decay faster than any polynomial in n, Okay, and so, for example, if you want to think about specific functions of n that decay faster than polynomials, you know, maybe something like that, or e to the minus n, or 1 over n factorial, right? So those are examples of things that decay faster than polynomials. And this gives you a nice way of constructing infinitely differentiable periodic signals, is to just choose some sequence that decays faster than polynomial, and you know, plug that in for the CDFT of f. That'll give you a function whose which is infinitely differentiable and t periodic, but isn't a harmonic function necessarily. Okay, and you know, for fun, so this is pretty regular, but what would be more regular than this? Well, you know, you might want f to be not just infinitely differentiable, but real analytic. Okay, all right. So there's another case. So if, in fact, this is if and only if f is real analytic. So remember, real analytic functions, I'm not going to dwell on this. I'm not going to go into a big long discussion about real analyticity, but if you know what real analyticity is, then this will mean something to you. Okay, so these are necessary and sufficient conditions for a signal to be periodic and real analytic, given in terms of the decay rates of the CDFT. Okay. So there's constants, C and alpha, such that CDFT of f is less than C e to the minus alpha. Okay. And so, you know, these examples of things that decay faster than polynomials, they'll work here. So in fact, these things that I wrote down here won't give you a signal that's just infinitely differentiable. It'll actually give you a signal that's real analytic. Okay. All right, good. So that is our discussion of differentiation in the CDFT. And so, like I said, there's 2 points here. One are formulas like this one, and like this one. Okay. But the other is you know, the list of conditions like this, okay, for relating properties of a signal to properties of its CDFT. And so, sorry, maybe what I'll do here before I leave is we'll look at some examples. Excuse me. Okay, and so the examples I'll look at are 2 that I looked at last time. So I had these 2 signals last time, and we calculated their CDFTs, and I had these signals specifically because they illustrate what's going on with this differentiation result. Okay, so the first one we called f, and it was defined on 0, 1. And between 0 and a half, it was 1. And between a half and 1, it was minus 1. All right. And then I had G. Okay, and again, it was 1 periodic. And it was defined by increasing with slope 1 from 0 to half on the interval 0 half, and then it decreased with slope -1 from a half to 0 from t equals a half to t equals 1. Okay, and the reason that I use these is that there's a formula that relates these things, and the formula, of course, is that g of t is the integral of f. Okay, so if you just integrate f, of course, you get g. And so this is a situation where g is absolutely continuous. So notice g is not differentiable. Okay, it fails to have a derivative at t equals a half, and when you periodically extend it, also at 0 and 1 and all integers. But nonetheless, it is the integral, indefinite integral of an integrable function, namely f. Okay, and so we know then that the CDFT of g will be related to the CDFT of f by a formula that we can predict. And so f is like the derivative of g. Okay, so what we expect then is we expect that we should get CDFT of f. Okay, is at n. Okay, is 2 pi I n over t, but t here is 1. So, okay, f CD of g of n. Okay, and indeed that was true, right? So this thing last time we calculated to be -1 to the n -1 over n pi I. Okay, and then this thing last time we calculated to be -1 to the n -1 over. Okay, and so now we know what the answer should be. If we know this, we know what this must be. Okay, and it's going to be, you need for the so the I is going to cancel with that I, and so you need a 2 pi, so you're going to get 2 pi squared n squared, right? Okay, so you get 2 pi squared n squared. Okay, all right, so this is an illustration that we saw last time of this sort of general condition about CDFTs, and so you notice here that f here is pretty irregular, right? So it's discontinuous, right? Really, about the only thing you can say about f. So it's piecewise continuous, but piecewise continuous isn't really a very nice regularity property because it's discontinuous generally. So really f is in L1. That's about L1 per. That's about the best you can say about f in terms of its general properties. And so what we see here is that its CDFT decays quite slowly, like 1 over n. Okay. All right, whereas g is continuous, at least, and it's in fact better than continuous. It's absolutely continuous on each period. Okay, and that's reflected in the fact that its CDFT decays faster than 1 over n, right? So it decays like 1 over n squared. Right? Okay, so we see a specific illustration of the general differentiation conditions showing up with these two examples. All right, good. So now let's talk about the CDFT and convolution. Okay, because there's a general thing that happens with certain transforms, the Fourier transforms being among them, which gives a nice relationship between convolution and the transform. Okay, so I'm just going to state the condition first for the CDFT of a convolution. Okay. So if F and G are in L1 per T. Okay, so now we hearken back to our discussion of convolution, and we remember that if F and G are in L1 per, then their periodic convolution exists. Okay, and moreover, the periodic convolution is also in L1. Okay, so that's a very nice sort of relationship for transforms, given that L1 is kind of the natural domain of the CDFT, and for all of our other transforms too. Okay. All right. Then. All right. So the point is that we can calculate then the CDFT of the periodic convolution, which I'll write like that. Okay. All right. So I know that this is in L1 per by our discussion about convolution. All right. So I can take its CDFT. Okay. And then the question is, what is the relationship between the transform of that convolution and the two CDFTs? Okay. And the answer is you get product. Okay, so this general rule is that transforming convolution in the time domain, in the frequency domain, or more generally in the transform domain, gives you product. Okay, so this happens with Fourier transforms, and it also happens with the Laplace transform. Okay, so this is our first glimpse of that for the one of our four Fourier transforms. Okay. All right, so I'll give a proof for this, and it's another application of Fubini's theorem, kind of course, because convolution is defined using an integral, and so is the CDFT. All right, so FCD of F star G T. So by definition, it's the integral from 0 to T, F star G T, e to the minus 2 pi T over T dt. All right, then I'm going to stick in the formula for convolution. Like that. Okay, so then what I want to do is I want to do a change of variable here. And so this one's a little bit easier, or you have to think about it less at least, than our previous application of Fubini's theorem, where we swapped orders of integration. And the reason is that we're just simply integrating here over the whole square from 0 to T. All right, so we can swap the order without having to think hard about the limits of integration. Okay, so I'm going to take I'm going to swap the order of T and S, and then so G with respect to the integral by T is constant. Okay, so I get the integral from 0 to T, G of S times the integral from 0 to T, F of T minus S, e to the minus 2 pi n T over T dt ds. Okay. All right, so it's obvious now what I want to do, right? This isn't quite the CDFT of f, because the argument of f is the shifted version. Okay, so I'm going to, I have the shift formula that I had before, but how did we get the shift formula? It's really just by a change of variable. And so I'm going to do a change of variable here. And I'm going to call this tau. Okay, right, so tau is going to be t minus s, and so t is equal to s plus tau. Right, so that's going to show up there. Okay. So the integral from 0 to t. And when you do the change of variable, you also have to keep track of the change in the upper and lower limits of integration. All right, and then when you do that, it's going to be the integral from minus s to s, sorry, t minus s. Okay, f of tau e to the minus 2 pi I n. And then up here, I'm going to get tau plus s over t dt. Yes, and now, of course, what I'm going to do is I'm going to take the e to the 2 pi I n s and outside the integral here. Okay. All right. So we leave it like this. And so now let's look at this integral here. This is still an integral over a period, right? I've just taken the period and I've shifted it by s. Okay. And so when I take this term out, I'm only left in here with a function of tau. And so I'm just integrating a function of tau over a shifted period. And so it doesn't matter what period I integrate with respect to. And so I can easily change that to this period. Okay, and now this thing is independent of s, right? So I could just pull it outside the integral here, and I get the desired formula that this is the product. Okay. So it's a nice, another nice application of Fubini's theorem. Now, okay, so the CDFT of a convolution is the product of the CDFTs. What about the CDFT of a product? Okay. So now we need some hypotheses on F and G. Okay, and you can see that pretty evidently because if you're going to take the product of two functions in L1, that's not necessarily going to be in L1 anymore. Okay, so as an example of that, you can take 1 over root t. Okay, so 1 over root t on the interval 0 t, that is in L1, right? So this is one of the examples we use for calculating integrals of unbounded functions, right? But then if you multiply this thing by itself, you get 1 over t, which is not integrable on L1. right? So you can't get away here with just F and G being in L1. You have to have some additional hypotheses, and we're going to give those. And so now there's no one rule which is going to work all the time. And what we're going to do is we're going to give the hypotheses on F and G, and the hypotheses on F and G will be so that the convolution of, sorry, not on F and G, but on the transforms of F and G. And the hypotheses are going to be so that the transforms are convolvable. Okay, and then what we're going to see is that the CDFT of the product is the convolution of the CDFTs, right? So the relationship between convolution and product goes both ways, okay? But in the one case, when you go from products to convolutions, you need additional assumptions, okay? So here's the result. So if F and G in L1 per are such that their transforms are in little L1 and this is quite a strong assumption. In fact, we're going to see this assumption show up when we talk about inversion of the CDFT, and it also, the condition also shows up when we talk about the DCFT. Okay, so this is a substantial and meaningful condition, but right now it's just kind of what we need for this result to be valid. Okay, so if it is valid, then first of all, FG is in L1. It's much stronger than L1. In fact, it's continuous. Okay, and the CDFT of FG T is the CDF. Sorry. The right. So it's the CDFT of F convolved with, okay, so now this is the aperiodic discrete convolution, all right, but it's still just convolution. So, all right. And you know, I'm not going to give the proof here. The proof here is actually very easy, and the proof is easy really because this condition is a very strong condition. Okay, but it kind of jumps ahead to things we haven't talked about yet. All right. Okay, so that's the basic things we're going to give about the L1 CDFT, all right, at least as a transform. But the next topic that we want to talk about is the inverse of this L1 CDFT. So first of all, does it even have an inverse? And if it has an inverse, what properties, is there a formula for that inverse? Under what conditions is that formula valid, and things of that nature. Okay, so these are all things we're going to start talking about next time. And this is really, in some sense, the real technical meat of the CDFT, because it touches upon a subject of what's known as Fourier series. Okay, so, but we'll get to that next time.